So, how is a day in the life of a solar astronomer? Well, the first thing we have to do is open the telescope right after sunrise. We have to do it very early in the morning, and we have to come here to the top of the tower to set up the instrument. What you see here is the turret, the upper part of the telescope. It holds the 1 meter lens, which is the main optical element of the Swedish 1 meter solar telescope. It's a black circle you see on the right. So now the telescope is pointing to the sun. Right now the motors stopped working, and as I said, we are atop the tower. It's a 30-meter tower. I'm going to show you the floor of this platform, and I think you can see it there. So the ground is very far from the telescope, and this is for one good reason. We want to avoid the heat produced by the sunlight during the day, which heats up the whole building, but also the ground. And we want to put the telescope as far as possible from these heat sources in order to prevent turbulence and maintain an excellent image quality. So here we are at the Roque de los Muchachos Observatory on La Palma, on the island of La Palma. In the background you can see the Nordic Optical Telescope, which is a nighttime telescope, and in the foreground you have the Dutch Open Telescope. It's an alien telescope mounted on a very special platform designed to avoid vibrations by wind. So it's also an open telescope, so the dome is foldable, leaving the telescope open in the air in order to minimize turbulence. Again, this is our enemy. We have to fight against turbulence. The other buildings down there are the residence and the magic telescopes. Now, you can also see the clouds below the observatory level. So we are at an excellent site for solar observations. Well, I'm going to show you the other side. This is the caldera. We are right at the rim of the caldera. This is the best place for solar observations in the observatory because the air flows here in a very smooth way without producing turbulence. We're gonna see the 1 meter lens here. It's unique. There are very few telescopes in the world featuring one lens as the main optical element. So this is a refractor telescope with no central obstruction, and it's well known for providing excellent image quality. What you see here is a small H-alpha telescope. We use it to observe the solar chromosphere at the same time we take observations with the main telescope. Now we are pointing to the sun, and we have to repeat this procedure every morning. It takes about 10 minutes because we have to remove the cover of the lens manually, and this is the cover. We use a special device which we have to move and put below the telescope to remove the cover, which protects the lens during the night. Okay, let's go to the control room and see how we start the observations. This here is the hole we use to go inside the building. You see a ladder there. We have to be very careful, and a very interesting device over there. Probably you can see it. It's a screwdriver, we use it to open the lid, this one, which is very heavy. I'm right below the telescope, and this is the tube that will take the light from the turret down to the optical lab, which is about 30 meters below. And as I said, we have to go down the ladder and then down the stairs every morning. Now we are walking to the control room, which is in the basement of the building. And this is the control room with my colleague Ricardo. Hi, Ricardo.
Hello.
Okay, so you opened the telescope. You started the instruments already?
Yes, I already ready calibrations of the flats for the AO and correlation tracker.
Oh, very good. Let me show you the live image from the sun we are getting from the telescope. This is the solar granulation, and you see that the image is not very stable because of the air turbulence, but we will, it's quite a good day with good conditions. We will be able to correct part of these distortions using a system called adaptive optics that will correct in real time the deformation of the images. So we are now observing after calibrating the instrument. Again, we have to do the calibration every day. It takes us about 10 minutes, but it's essential to have the instrument ready for observations. So again, let me come closer to the screens with the live image from the sun. Now we are observing an active region on the surface. It consists of several pores, which are small sunspots without a penumbra. And these here are observations in the ultraviolet, in the calcium 2H line. Well, this is the control room with lots of computers. As you can see here, this is the main computer controlling the instrument. But we also have here a couple of other devices and systems which are also very important for the observations.
So on your left hand side you have the AO control system. So there you see these individual small squares that basically they probe different patches on the entrance of the telescope. On your next screen you have the correlation tracker, and this device is there to correct displacement or global displacements on the image. So you have a place where you can define the target, and then running a very fast camera with 3000 frames per second or up to 3000 frames per second, you can identify these movements or displacements and then correct them. On the third screen you have our, let's say, coordinate system, where we can point the telescope to several different locations. At the moment, as you see here, I hope you can see the mouse, you have this small square that correspond to the location of the sun where we are pointing at, and then just simply by clicking in different locations, the system points automatically to those locations.
So we can point anywhere on the solar disk, right?
Anywhere on the solar disk, including a little bit out of the limb. The limb of the sun is represented here by this green line, and we sometimes point there because they are structures that are visible at these locations. I can try to change the filter that we are looking with this image that is not identified in this telescope or observing this telescope, but with a different instrument. in this case STO, and you can see here that we have several different structures around the sun, and you can also point there and observe them individually.
And we have the last screen in the control room here. What is this, Ricardo?
This is a live image based on H-alpha telescope that we also have installed on the top of the tower, and we use it basically to guide ourselves in case we are interested in some specific structure that we observe in the H-alpha.
And again, the screen for the adaptive optics system. This is really the main system in the telescope because it corrects in real time the distortions introduced by the Earth's atmosphere. It's not perfect. Sometimes it does a good job, other times it cannot correct the image when the seeing conditions are bad. You see that we have the same image of the solar surface repeated, I think it's about 80 times here. And from the motion of these individual images, we can determine the corrections to be applied. And well, here we have a big screen with all the data corresponding to this observation. We also have weather station data and some weather predictions to know if the conditions will be good or bad today, but also tomorrow. We continue our observations. Now the quality is not bad. Here we have two different instruments. We are using the CRISP instrument and the CHROMIS instrument. The CHROMIS instrument is in the first row of screens. The CRISP instrument is below, and we observe the same region of the solar surface in different wavelengths, in different colors, in order to determine the properties, the physical properties of the solar gas. For example, the temperature, the density, the magnetic field, the velocity of the gas, etc. This image here tells us the image quality as a function of time during our observations, and the green curve shows how good the image is. You see that we started the observations at around 721 here. We had relatively good image quality, then it decreased, then it went up a bit, then it decreased, and here it started to pick up again. But the image quality has degraded over time overall. So, well, it's not, probably it's not a good day for observations today, but we will keep trying. Okay, we are observing right now and the conditions are very good. As you can see on the screens here, the differential motion has decreased a lot, and we have very sharp images. On the upper right screen, you see lots of brightenings in the active region, so something interesting is going on there. After 3 hours of observations, we are getting the best sequence in the morning. This is a quiet sun region. You can see the granulation, convective cells that are bright, surrounded by narrow intergranular lanes, which are cooler and where the gas goes down into the solar interior. And as you can see, there's no differential motion. The image looks very sharp, and there are very, very small motions compared with this morning observation of the active region with the pores. Yeah, it's a very good sequence. This is a very good sequence. Still, during some moments, the scene degrades and the image quality goes down a bit, but it quickly recovers. What is the R0 now, Ricardo?
44.
44. This is among the best you can get at the Swedish Solar Telescope. You can even see the bright points in between the granules, and these bright points are magnetic field concentrations, very tiny magnetic field concentrations, maybe 100 kilometers, 200 kilometers in diameter. Yeah, this is a live image, and it's really quite amazing. What is the R0?
Now it's 27.
27. We reached almost 50, which is excellent. Now it's time for calibrations. We need to take flat fields in order to remove all the artifacts on the cameras and get perfectly clean images. This flat field procedure, in which we move the telescope around the disk center to produce a uniform field concerning illumination, takes about 2 hours. And during this time we cannot observe, we just calibrate the observations. So I'm going to take the opportunity to show you 2 more rooms. These are the computers running the cameras and storing the data. We have terabytes of storage, and this is needed to really save in real time all the data that is being taken. This room has to be cooled down to about 20 degrees centigrade because of all the equipment which is working continuously. This is the electronic lab. A bit messy, but all the equipment is repaired here on the spot in case it's necessary to continue the observations. It's the end of the day, and now the scene has degraded a lot. We won't continue the observations. It doesn't make sense now. You can see that the image is completely blurry because of the scene. It's late in the afternoon, and both the building and the ground are very hot now, producing turbulence and ruining the image quality. So we are going to close the telescope now and transfer the data to our institute. Before we do that, let me show you the optical lab. Yeah, this is the core of the telescope. I'm going to show you the tube, the end of the tube. This morning we saw the tube upstairs. It has about 30 meters in length, and this is the edge of the tube near the basement of the building. So the solar light comes here and produces an image right at this position. This is the sun and the focal plane of the telescope. Inside this box we have the deformable mirror of the adaptive optic system and the flat mirror of the correlation tracker that keeps the image stable despite the vibrations induced by the wind. Now the light comes into the box from above, and then it goes in this direction And we have a lot of optical elements there to split the light in different wavelengths, in different colors. So the blue light goes to this instrument here, the big silver container over there, which is a filtergraph. It allows us to take images of the solar surface in different colors through a very narrow range of colors. We call them monochromatic images. This instrument is called CHROMIS, and we use it to observe the solar chromosphere. Behind CHROMIS, we have a new instrument at the Swedish Solar Telescope called HESP. This is a classical spectrograph used to measure the helium line at 10^830 angstrom. It's an amazing instrument, still under construction. It's not operational yet. It has 4 CCD cameras, one camera, another camera, and there's another one down there. So these cameras are really fast. For the near infrared, they have to be cooled, and they are very expensive. The 4 cameras cost about €1 million. Amazing, right? And finally, we have here the second instrument we use today, the CRISP instrument. Again, it's a filtergraph allowing us to select very narrow parts of the spectrum to make monochromatic images of the solar surface. These are very sensitive optical instruments. They are controlled with electronics, which are mounted on these racks next to the edge of the telescope tube. By the way, do you see those tubes, those pipes coming to the edge of the telescope tube? This is the cooling system. We are pointing to the sun and producing a lot of heat inside the tube. The tube is in a vacuum, so there's vacuum inside. We have extracted all the air in order to prevent heating and turbulence inside the tube. But the sunlight hits the metal parts inside the tube and rise the temperature. So this is why we need a very effective cooling system, which is provided by these pipes, cooling pipes. I hope you have enjoyed this tour. I hope you will become interested in solar physics, and who knows, maybe you will become solar astronomers in the future.